We thought we understood 3IATLAS. It came from outside. It was a comet. It swept through our solar system, passed close to the sun, and left. Case closed. Except it is not closed. Because the longer scientists study the data they collected during 3IATLAS's visit, the stranger it gets. The water inside it should not exist. The methane it released should not have come from where it did. Its trajectory carries statistical odds that keep making astronomers uncomfortable, and the chemical fingerprints embedded in its gas now being decoded by some of the most powerful. Telescopes on Earth and in space are pointing to a birthplace so cold, so ancient, and so completely unlike our own solar system that scientists are now saying this object is literally from a different chapter of the universe's history. 3IATLAS. It just got stranger, and we need to talk about all of it. Let us start with the water, because water seems simple. It is 2 hydrogen atoms bonded to 1 oxygen atom, H2O, something every child learns in school. But there are different kinds of hydrogen. The most, neutron. Water made with deuterium instead of regular hydrogen is called heavy water, or semi-heavy water when only one of the 2 hydrogen atoms is replaced. It is heavier. It behaves slightly differently. And crucially, the amount of it in any body of water acts like a chemical thermometer. It records how cold the environment was when that water originally formed as ice billions of years ago. Extremely cold environments produce ice with much higher concentrations of deuterium. So, the ratio of deuterium to regular hydrogen in a comet's water is a direct measurement of the temperature of the region in space where that comet was born. Here is where 3IATLAS breaks everything we expected. A team led by doctoral student Luis Salazar-Manzano at the University of Michigan used the Atacama Large Millimeter to SOS submillimeter array, one of the most sensitive radio telescope networks in the world, to measure the deuterium content in the water being released by 3IATLAS as it traveled through our solar system. The findings published in Nature Astronomy in April 2026 revealed something that stopped the entire field cold. The deuterium to hydrogen ratio in 3IATLAS's water is more than 40 times the value found in Earth's oceans. It is more than 30 times the value found in any comet in our own solar system. The lead author said it plainly. It is more than 40 times the value in Earth's oceans and more than 30 times the value in solar system comets. That is not a small deviation from the norm. That is not an unusual measurement that sits on the edge of known ranges. That is something that falls completely outside the entire range of anything we have ever measured before in our planetary neighborhood. The water inside 3IATLAS forms somewhere so unimaginably cold that our solar system's most frigid regions cannot even begin to explain it. The research team concluded that wherever 3IATLAS was born, it formed in an environment dramatically colder and with far less radiation than the region of space that gave birth to our solar system. The conditions that created the planets and comets and asteroids in our neighborhood are nothing like the conditions that created this object. Our solar system's formation story simply does not apply to 3IATLAS. It is not just from another star system, it is from a fundamentally different kind of place at a fundamentally different moment in the galaxy's evolution. That last part is critical because a second major study, published in Nature Astronomy in July 2026, took a completely different approach to the same question of where 3IATLAS originated. Astronomers led by Cyrielle Aupetom at the University of Edinburgh used the European Southern Observatory's Very Large Telescope in Chile to measure the isotopic ratios of carbon and nitrogen in 3IATLAS's coma. Not hydrogen and its heavy version, but carbon and nitrogen. Different elements, different measurements, different physical data entirely. And they found the exact same alarm going off from a completely independent direction. The carbon isotopic ratio they measured, comparing the lighter and heavier forms of carbon, came out at approximately 147. The nitrogen isotopic ratio came out at approximately 343. Both of those numbers are substantially above the baseline values found in any solar system comet ever measured. Carbon in our solar system comets typically sits around 90. Nitrogen typically sits between 130 and 170. The VLT measurements for 3IATLAS put it completely outside the range of every comet formed in our solar system. The values are consistent, say the researchers, with formation in a metal-poor, ultra-cold environment in an earlier, less chemically enriched Milky Way. Let that land for a moment. Metal-poor means the star that this comet formed around was born when the universe was very young, before generations of massive stars had lived, died, and exploded in supernovae that spread heavy elements throughout space. Every time a massive star dies in a supernova, it seeds the surrounding gas with heavier elements, like carbon, nitrogen, oxygen, and iron. Over billions of years, the Milky Way has been getting progressively richer in these elements as more and more stars complete their life cycles. Early stars formed when the galaxy was young and metal poor. They formed from pristine material that had not yet been enriched by stellar deaths. Their planetary systems and their comets would carry the distinct chemical fingerprint of that ancient metal-poor environment. The carbon and nitrogen ratios in 3I-ATLAS point to exactly that kind of origin. It is a comet formed around a star that was itself born in the early universe when the Milky Way was young and unprocessed. Researchers co-authoring the study noted that 3I-ATLAS represents a mind-bending opportunity to probe the composition of another planetary system, one that formed long before our sun and solar system even existed. The star 3I-ATLAS likely formed around, existed at a time when the galaxy itself was vastly different. The sun is approximately 4.6 billion years old. The estimated age of 3I-ATLAS, based on both its hypervelocity and now its primordial chemistry, is somewhere between 10 and 12 billion years. That means this object's ice, the water, carbon compounds, and methane, now being analyzed by our instruments, crystallized more than twice as long ago as the Earth has existed. Before our solar system had even begun to collapse from its nebular cloud, 3I-ATLAS was already an ancient interstellar wanderer. Now we come to the James Webb Space Telescope and what it uncovered when it locked onto 3I-ATLAS with its powerful mid-infrared instruments. After 3I-ATLAS passed perihelion in late October 2025, the James Webb Space Telescope turned its MIRI instrument on the retreating comet on December 15th, December 16th, and December 27th of 2025, when the object was between 205 million and 236 million miles from the Sun. The results, published in the Astrophysical Journal Letters in June 2026 by a team led by Matthew Belyakov at Caltech, produced the first mid-infrared chemical fingerprint ever taken of any interstellar object in history. The measurements confirmed the expected presence of water vapor, carbon dioxide, and carbon monoxide. But then came the true shocker: methane. For the first time in scientific history, methane gas was directly detected outgassing from an interstellar visitor. This methane was not sitting on the exterior surface of 3I-ATLAS. If it had been sitting on the outer layers, the billions of years of harsh cosmic radiation that 3I-ATLAS experienced during its endless journey through interstellar space would have destroyed it long ago. Methane is extremely volatile. It sublimates easily, changing from ice to gas at temperatures far colder than water requires. Its presence in the outgassing after perihelion means it was buried deep, hidden beneath thick, protective layers of surface material, insulated from starlight until the comet passed close enough to our sun for solar warmth to finally penetrate those deeper icy chambers and unleash the methane locked away for billions of years. This is a comet that had ancient methane preserved in deep interior vaults, sealed for most of the history of the cosmos, and finally cracked open by our sun as 3I-ATLAS passed through our neighborhood. The methane production rates measured by Webb were staggering. In two separate observation periods, methane was being produced at rates of 13.7% and then 27% of the water production rate. In our own solar system's comets, those high ratios are virtually unheard of. Earlier pre-perihelion Webb observations had already shown that 3I-ATLAS had an extraordinarily high ratio of carbon dioxide to water, with CO2 carrying roughly 87% of the total gas phase mass loss. Even that ratio was unusually high compared to solar system comets. And then post-perihelion, methane emerged from the depths at levels never before recorded for an interstellar body. The chemical portrait building up of 3I-ATLAS is of something genuinely alien, not in the science fiction pop culture sense, but in the precise scientific sense of the word. It is foreign from outside, composed of different materials and wildly different ratios formed under vastly different conditions from a completely different era of cosmic time. The water is too heavy, the carbon is too heavy, the nitrogen is too heavy, the methane was buried too deep. Everything about this object's chemistry is skewed in the exact same direction, toward conditions that are far older, colder, and less chemically enriched than anything found in our home system. And then there is the question that mainstream astronomy handles delicately, but that refuses to go away: the question of its trajectory and mechanics. Harvard astrophysicist Dr. Avi Loeb has cataloged what he calls 22 separate anomalies in 3I-ATLAS's behavior, trajectory, and physical properties. He has written extensively about these points, while the overwhelming scientific consensus, including NASA's official position, is that 3I-ATLAS is a natural comet. The anomalies highlighted by Loeb are grounded in real measurements, real data points, and published telemetry, even if the interpretation sparks intense debate. Consider the orbital alignment. The retrograde trajectory of 3I-ATLAS is aligned to within 5 degrees of the ecliptic plane, the flat disk in which all 8 of our planets orbit the Sun. The Milky Way's galactic disk is inclined about 60 degrees relative to our ecliptic plane. If you randomly picked a direction in space for an incoming interstellar object to arrive from, the statistical odds of that direction being within 5 degrees of our ecliptic plane are about 0.2%, or roughly 1 in 500. The object arrived from one of the very few precise vectors that would thread it directly through our planetary system as neatly as possible. Then look at the non-gravitational acceleration, the extra push of speed that 3IATLAS experienced beyond what the pure gravitational pull of the sun could explain. This push is expected for a comet, releasing expanding jets of gas, but the jets observed on 3IATLAS were described as tightly collimated, meaning exceptionally focused and directed, rather than diffuse and scattered as you would expect from a simple, irregular icy body sublimating randomly in all directions. High-resolution Hubble Space telescope images revealed not just 1 or 2 loose streams, but what appeared to be 3 symmetrically separated mini-jets in addition to a broader coma. These jets remarkably maintained their geometric orientation across 1 million kilometers in multiple directions despite the measured rotation of the nucleus. Natural jet systems on standard comets tend to wobble, shift, and flare as the uneven surface rotates through changing solar illumination angles. These jets remained bizarrely stable. And then there is the mathematical anomaly of the Jupiter flyby. When scientists calculated where 3IATLAS would pass Jupiter on March 16, 2026, taking into account all of its observed non-gravitational acceleration, the forecasted minimum distance from Jupiter was 53.6 million kilometers. Jupiter's Hill radius, the exact boundary at which Jupiter's own gravity overcomes the Sun's gravitation, altitude, and can hold objects in orbit, was calculated to be 53.5 million kilometers on that exact date. The two numbers were virtually identical within a margin of 60,000 kilometers, which sounds large to a layperson, but is an absolute razor-thin margin in celestial mechanics. The odds of a random incoming object passing Jupiter at precisely its Hill radius by pure mathematical coincidence are extremely low, calculated by Loeb at roughly 1 in 25,000. Now, Loeb is a respected astrophysicist at Harvard, but his willingness to publicly discuss artificial origins has made him a lightning rod for controversy. Most astronomers do not share his radical interpretation. They emphasize that apparent coincidences naturally accumulate when you analyze enough data variables, and that explaining 3IATLAS as a natural comet does not require inventing new physics or alien technology. Furthermore, the SETI Institute and Breakthrough Listen conducted an exhaustive radio search using the Allen Telescope Array, sifting through nearly 74 million potential signals. They flagged 201 candidates that survived initial filtering, but every single one was definitively identified as human radio frequency interference or terrestrial satellite noise. No narrowband alien transmissions above 10 to the 11th power watts were detected in any frequency band. NASA's official stance remains resolute. 3IATLAS is an exotic natural comet. Yet what makes this revelation so compelling is that, regardless of the theoretical debate, the underlying physical anomalies are completely real. The 5-degree ecliptic alignment is a verified orbital calculation. The collimated stable jets are visible in Hubble data. The Jupiter Hill radius match is confirmed in orbital physics tracking. The extreme chemical makeup is verified across multiple world-class observatories. The water's deuterium level, sitting 30 to 40 times higher than solar system norms, is not a rounding error. It is a clear physical signature from an entirely different environment. The methane was sealed deep enough to survive cosmic radiation for eons. The carbon and nitrogen isotopic ratios fall entirely outside the known domain of solar system comets. If 3IATLAS is natural, and again the global scientific consensus insists that it is, then what we have encountered is an object that proves the galaxy is far more diverse in its chemistry and history than our local neighborhood could ever reveal. We have spent centuries studying comets from our own solar system, bodies that all form from the same primitive cloud around the same star at the same time. 3IATLAS formed. Somewhere else, around a long-dead star that existed before our sun was born, in a colder, older, and chemically unrefined corner of a young Milky Way. When its deep interior ice began outgassing under the heat of our sun, it handed humanity a direct chemical sample from an ancient world we could never hope to visit. The Subaru telescope atop Mauna Kea in Hawaii observed 3IATLAS on January 7, 2026, as it emerged from solar conjunction after perihelion. The focus of these observations was the deep internal composition brought forth as intense solar heating unlocked interior ice layers. The ratio of carbon dioxide to water measured by Subaru was lower than pre-perihelion space telescope readings had shown. This shift revealed something vital. The outer layers and the inner core of 3IATLAS have distinctly different chemical structures. The outer crust, baked and modified by billions of years of interstellar cosmic rays, had eroded away. What spewed out post-perihelion was material from the pristine interior core. sealed off from external radiation since the dawn of the universe, and even that pure interior proved chemically distinct from anything in our solar system. Concurrently, the European Southern Observatory's Very Large Telescope captured remarkable time-lapse imaging of 3IATLAS on January 18th and February 18th, 2026, using its FORS 2 instrument. Across observation windows spanning about 14 minutes, the comet moved rapidly against background stars that appeared as long trailing streaks. Although its brightness had faded significantly from its peak near perihelion, the coma remained wildly active, shedding ancient gases into the solar wind. By March 2026, it swept past Jupiter and began its final outbound leg. Moving outward at an unmatchable velocity of over 60 kilometers per second, it has already passed beyond the outer gas giants and is receding back into interstellar space. It will never return. It has gone forever into the dark, but it left behind a scientific treasure trove unmatched in the history of astronomy. Virtually every major observatory participated in tracking this visitor: Hubble, James Webb, Subaru, the Very Large Telescope, the Atacama Large Millimeter Submillimeter Array, and even the Europa Clipper spacecraft, which managed to capture crucial ultraviolet spectral readings, while Earth-based instruments were blinded by the sun's glare near perihelion. Scientists are still actively analyzing these massive data sets. Research papers covering dust composition and isotopic modeling continue to roll out, filling in the details of an extraordinary cosmic puzzle. What is already beyond dispute is that 3IATLAS has permanently altered planetary science. It has provided physical proof that our solar system is not the baseline template for the universe. The conditions under which our planets, oceans, and comets formed are not the universal standard. Somewhere in deep space, around an ancient metal-poor star that may have burned out eons ago, a planetary system formed under temperature so cold that water ice locked in deuterium at 40 times the concentration seen in Earth's oceans. Carbon and nitrogen forged isotopic ratios unlike anything in our solar system. Methane accumulated in deep interior vaults and remained frozen for over 10 billion years, long enough for our sun to form, for Earth to coalesce, for life to evolve, for human intelligence to build advanced telescopes, and finally for astronomers to intercept this single frozen traveler as it zipped through our backyard. We have now detected 3 distinct interstellar objects passing through our solar system. Oumuamua in 2017, which was caught late and left behind baffling propulsion questions. 2I, Borisov in 2019, which closely resembled a familiar local comet. And 3IATLAS, by far the largest, brightest, most thoroughly observed, and most scientifically perplexing of them all. Each visitor was fundamentally different from the last. Each one told a unique story about the vast diversity of the cosmos, and each was detected only because our modern sky survey technology reached a threshold of sensitivity where catching these high-speed intruders became possible. This technological evolution is accelerating. The VRC Rubin Observatory in Chile, equipped with a monumental 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy, scans the entire visible southern sky every 40 seconds. Astronomers anticipate that this revolutionary facility will dramatically transform interstellar object detection. Instead of catching one isolated visitor every few years, we may soon be discovering several every single year. Each discovery will represent another physical sample from a distant star system, another message in a bottle washed up on our cosmic shore from a world we could never reach in person. 3IATLAS did not simply pass through our solar system. It fundamentally expanded our understanding of how varied and ancient the universe really is. Its water chemistry defied our models. Its methane was buried in deep primordial layers, sealed before the Earth existed. Its elemental ratios were forged in a galaxy far younger and colder than the one our sun was born into. And the anomalies in its trajectory, its precise alignment to our ecliptic plane, its tightly directed structural jets, and its razor-thin pass near Jupiter's Hill radius will spark passionate scientific debate for years to come. Think about what it means that we are living in the era where these discoveries are happening. For almost all of human history, the idea of material traveling between different star systems was purely theoretical. The distances separating stars are so mind-bogglingly vast that the human mind can barely comprehend them. Proxima Centauri, our nearest stellar neighbor, sits over 4 light-years away. At the speed of our fastest current space probes, it would take tens of thousands of years to cross that distance. The probability that a comet could be ejected from its home system, drift through the void for 10 billion years, and cross our solar system at the exact moment humanity possessed the technology to track and decode its light seems almost statistical fantasy. Yet it has happened 3 times in less than a decade. The sudden influx of these discoveries does not mean interstellar objects are a new phenomenon. They have been silently sweeping through our solar system for billions of years. We were simply blind to them. We lacked the wide-field digital sky surveys, the automated detection algorithms, and the space-based infrared telescopes needed to spot a faint, fast-moving point of light against the background stars. The ATLAS survey that first spotted 3IATLAS was built to scan the skies for potentially dangerous near-Earth asteroids to protect our planet. Instead, it stumbled upon an ancient ambassador from a distant star system. What changed was not the universe, but our capacity to see it. We developed better eyes, and the moment we looked deeper, we discovered that reality was far more complex than our theories had assumed. What keeps scientists fascinated about 3IATLAS is how it shattered expectations. When Oumuamua arrived, it was a mysterious outlier that fled before we could get detailed spectra. When Borisov arrived, it felt comfortably familiar, reassuring scientists that interstellar comets mostly behave like local ones. But 3IATLAS, the third visitor, was vast, luminous, chemically complex, and completely foreign. Its extreme deuterium levels, its ancient metal-poor isotopic signature, its structural jets, and its deep methane vaults demonstrate that planetary systems across the Milky Way form under physical conditions far more diverse than our local solar system ever suggested. Every interstellar object we track and analyze becomes a free sample of an alien world. We do not need to build interstellar starships taking thousands of years to reach distant suns. The galaxy is delivering pieces of those distant systems directly to us. As telescopes like the Vera C. Rubin Observatory come online, we are standing on the precipice of a new era in astronomy, one where we map the chemistry, history, and physical diversity of the entire galaxy by reading the frozen messengers that drift through our sky. 3IATLAS was a wake-up call from the deep cosmos. Its water was unlike any water ever measured on Earth. Its interior held pristine ice, sealed away before our planet was even a cloud of dust. Its chemistry was forged around a star that lived and died in a younger, colder galaxy. As it hurtles back out into the endless dark, never to return, it leaves behind a profound truth. The universe is far older, stranger, and more mysterious than we ever imagined, and our journey to understand it has only just begun.